Welcome to this concept bite. This is a short concept bite covering essentially the principles behind measuring very short lifetimes for the technique of TCSPC. So TCSPC is time correlated single photon counting. We collect individual photons after certain periods of time between our initial excitation pulse and the arrival of the photon at the detector. So hopefully just remembering that we usually expect to see fluorescence emission behaving like a nice first order decay. It might have one or two components, but we are expecting to see a nice first order decay. For fluorescence, this decay is usually on the timescale of nanoseconds or picoseconds. And so it's much too fast in order to use our more traditional detection methods. If we're looking to see this excited state fully deactivate, just you can see I've drawn the boxes of the first, second, third and fourth half-lives. Essentially we need to be leaving 5 or 6 lifetimes so that we end up with all of our sample back to zero, back to the background. Because we don't want to see photons arriving from a previous pulse. So we wait sufficiently long that hopefully all of the light arriving is from the particular pulse that we're looking at. So if I look at this in terms of what results I see in the data, well, I essentially have time moving across, and each of these lines is an individual experiment, an individual pulse of light. And you can see that I have photons, signals arriving at different time periods. And you can also see that on some of my lines, I don't have any photons arriving at all. This is pretty typical for TCSPC. We would normally expect to not have a photon arriving every time because we don't want to saturate our detector. And so having 100 different excitation pulses and only seeing one photon would not be considered unusual in this technique. We only want one photon to reach the detector. That's really important. And what we do is we set our detector with a fixed time, with that time essentially that it would take 5 or 6 of our lifetimes. So we have a quick guess and we run an experiment and we get a better guess and we're able to kind of hone our experiment features slightly. So how do we do this? Well, we use this thing called a TAC. I will refer to it as a TAC, but TAC stands for time to amplitude converter. What this is it's taking the time delay between the excitation and the emission pulse and converting that into an electrical signal. What it's doing is it's actually charging a capacitor, and it charges the capacitor as a linear increase in voltage across the capacitor. And so if, for example, I have my capacitor which runs between 0 and 10 volts, it would increase linearly between those 0 and 10 volts. So just as an example, if I had something with a lifetime of 2 nanoseconds, I would want to have a TAC time 5 or 6 times longer than that. And so I would want to have a TAC charge time about 10 nanoseconds, a bit longer. If I look at that in terms of what's happening, so if my TAC is charging between 0 and 10 volts, then if my photon arrives after 3 nanoseconds, I would expect to see 3/10 of my total time. So I've set my total time for 10 nanoseconds, my photons arriving after 3 nanoseconds. I would expect to see a TAC stopping when the applied voltage is 3 volts. If it's 6 nanoseconds, it would be 6 volts. I've said in passing that the TAC is a capacitor. Now capacitors take charge, they store charge, and we need to ensure that we let that charge drain away so that my signal, my applied potential, is always starting from 0 each time. So we need to give our capacitor time to decharge, time to discharge. And we refer to the time it takes for the capacitor to discharge as the dead time. And we take this time as if the capacitor had been allowed to fully charge. So it's no good me giving it enough time if it can drain away from 3 volts. I need to make sure that it's got time to fully drain from the 10 volts. And so I need to make sure that it's the maximum possible voltage that can be applied. So if I just look at this in terms of an example problem, let's say I've got a chromophore, it's got an average lifetime of 3.2 nanoseconds. And after calibration, I can see that I'm collecting 1 photon for every 10 scans. So what I'm saying is suggest a suitable frequency for the excitation pulses and suggest a suitable dead time for the TAC system. So let's just look at this, break it down. So I'm taking 3.2 nanoseconds and I'm saying, well, 6 lifetimes is about 20 nanoseconds. It just makes my numbers easy. That's all I've done. But I've gone 5 or 6 lifetimes and come up with about this 20 nanoseconds. And so I'm saying that my excitation pulses should not occur any faster than 1 pulse every 20 nanoseconds. I want to make sure it's all decayed. And just converting this 1 pulse every 20 nanoseconds into a frequency, well, that's 50 megahertz. Given that 1 in 10 photons is arriving at the detector, then I'm looking at a detection rate somewhere closer to 5 megahertz, which means that my 5 megahertz, again, just converting that back to my time, it takes about 200 nanoseconds to be able to record my data. In other words, my TAC needs to be fully discharged in about 200 nanoseconds. TACs with dead times longer than this, for example 1 microsecond, won't be discharging. They won't be starting at 0, and so they're no good. And so they can't accurately record the data. So my TAC must have a shorter time. And so anything suitable than 200 nanoseconds would be good, but let's say a TAC with a dead time of 120, which just happens to be a TAC I've used in the past, had a dead time of 120 nanoseconds, or anything shorter would be suitable. I hope this video has been helpful. I'll be back with more.